Okay. All right. So last time where we were at was we had laboriously written down the Euler-Lagrange equations for the kinetic energy Lagrangian, and we'd gotten them into a certain form, which I claim is a useful form, and that form involved these rather complicated expressions for what I call the Christoffel symbols for the Levi-Civita affine connection associated to the kinetic energy metric. Okay, so what we're going to do is spend the next few weeks putting together all of the tools we need to understand that string of words that I just spit out. Okay, and we will start that by talking for a few lectures about vector fields. So we've introduced the idea of a vector field previously, but we didn't really do very much with it. We mainly introduced vector fields so that we could talk about the standard basis vector fields, partial by partial X vector fields, which formed a basis for each tangent space in some coordinate chart. Okay. Now we're going to see that vector fields have associated with them lots of structure, and that structure is going to show up when we start talking about all of the things that we need to talk about, especially affine connections. Okay. All right. So let's remember what a vector field is. Okay, so a vector field is a mapping. Okay, and so I'm going to, if I don't say anything else, I'm assuming that it's infinitely differentiable or smooth. And if I want to say more about that, then I will explicitly say what its regularity is, like C1 or C2 or something like that. Okay, so if I don't say anything, it's smooth. So it's a mapping. Like so, such that when you evaluate this vector field at a point X, you get a vector in the tangent space at X, right? And so I drew a picture associated with this. So here's our manifold, okay? And so the idea was that at a point X, you had a tangent vector at that point. Okay, and then you had this process at every point. Okay. All right, so that's what a vector field is. So now we'll see that vector fields can be used to do a lot of different things, and the first one is this. So we're going to define this notion of what's called an integral curve for a vector field X. Okay, I don't remember if I introduced this notation, but I'll do it now. The space of all vector fields of class CR, so R times continuously differentiable vector field. So R for us will be in okay, thank you. Is denoted by the symbol. So I have a capital gamma R of TM. Okay, so that's the notation we're going to use for the set of vector fields. Okay, so gamma means set of all things, R specifies its differentiability, and Tm means that we're looking at things that are tangent bundle valued. Okay. And so again, just for concreteness, I'm going to talk about infinitely differentiable vector fields. Okay, so an integral curve for a vector field X is a curve gamma in M satisfying gamma prime of T. Okay, so the tangent vector to gamma, to the curve gamma at time T is equal to X at gamma of T. Okay. All right. So associated to this, of course, is a picture. Okay. So I have a curve gamma, like so, let's say. And so I know that gamma prime at T is the tangent vector field to that curve. So let's say I'm at this point here, which is along the curve, which will be some gamma of T for some T. And then I know that gamma prime of T is the tangent vector field to the curve. Maybe it looks like that. Okay. And I know that if gamma is an integral curve, that it must be equal to that. Okay, so what this means is that so I have the curve gamma, which satisfies this condition, which I have represented at a single time T like this. And so of course, this has to happen at every point along the curve. Okay, and so this is for every T in the interval I. Okay, now the thing is, of course, that the vector field is defined everywhere. Like so, okay? And so this is kind of a, and so the picture here is that you find a curve that kind of, fits itself nicely to the tangent vector field in the sense that it passes through every point along the curve with the velocity prescribed by the vector field X, okay? All right, so there's an obvious question here, and that is if you think about trying to fit such a curve to a field of tangent vectors, it's not immediately obvious that you can do that, first of all. Second, it's not obvious that if you do that, let's say you pass through X with the right tangent vector, that uniquely prescribes the curve gamma. So there may be some other curve gamma which passes through there with the same tangent vector. And so there's an existence and uniqueness question associated to the notion of an integral curve. Okay, and so to answer this question, I'm going to reduce this to something you already know about. Okay, and to do that, we're going to work in a coordinate chart. Oh, sorry, I'm working on a manifold here, so I'll use X's. Okay, so remember that this is short form for saying that I have a chart U phi, and I name its coordinates x1 up to xn. Okay, now let's write down the defining condition for an integral curve in coordinates. Okay, so the curve gamma is given in coordinates by T goes to x1 of t, xn of t. Okay, so that's the local representative of the curve in this set of coordinates. And so, of course, I'm assuming that the curve gamma, runs through my coordinate chart. If it doesn't, then there's nothing to talk about. Okay. The vector field x is given in coordinates by the usual way that you write a vector field in a coordinate chart. So x is xj, d by d xj. Okay, so you write it in terms of the basis vector fields, d by dxj, in the usual way. And then the capital xj's, these are what we call the components of x. Okay. All right, so now let's write down the condition to be an integral curve. The condition gamma prime of t equals x at gamma of t reads in coordinates, of course. Okay, so we decided when we introduced this notation for gamma prime that gamma prime at a time t was the tangent vector at gamma of t, whose components were just the time derivatives of the of these functions x1 of t up to xn of t that defined the curve. Okay, and so gamma prime of t is represented in coordinates by x dot j of t. Okay, and now this is a tangent vector. And so I can write it as a sum of the basis vector fields. Okay. All right. So this thing is a tangent vector at the point t, gamma of t, m. Okay. So in my picture here, it would be this tangent vector. Okay. In the tangent space at gamma of t. All right. So that's gamma prime. Then I'm going to write down the vector field x, but I'm going to only evaluate x at points gamma. Okay, so this is going to read xj at x1 of t. So I'm being very explicit here, filling this out completely. D by d, oops, dxj. Okay. So that's just literally the equation gamma prime equals x at gamma. Okay, and now because those coordinate vector fields d by dxj are linearly independent, that means that equality of these vector fields implies equality of the components on each side. Okay, and so this implies that x dot j of t equals x at x1. And so I'm going to be, I'm going to not use summation convention notation here in order to try to make the interpretation of this clear. I'm going to write this out component by component, starting with the first component. Okay, then you have also, of course, x dot 2 of t is x2 and up to x dot n. Okay. All right, so the reason I wrote it like that is that I hope that that looks familiar to you. Is that a thing that you've seen before? How about if I write, instead of x, I write f, okay? And instead of the vector x1 through xn, I write the vector, a single vector symbol x, and then I rewrite this as x dot of t equals f of x of t. Does that look familiar to you? What kind of a thing is that? It's an ordinary differential equation, okay? And so what this shows us is that the condition, okay, and so the point is that these are ODEs. Okay, they're not necessarily particularly pleasant ODEs. For example, they won't necessarily be linear. Okay, they're ODEs. Okay, and so the point is the condition when you write it down in coordinates for an integral curve, which is just that, when you write it down in coordinates, amounts to exactly this ordinary differential equation. And so then the question of existence and uniqueness, at least locally, boils down to the question of existence and uniqueness of solutions of ordinary differential equations. Okay. Do you remember from your ODE class or some other class what conditions you need on, on F, which for us is these things, in order to ensure existence and uniqueness of solutions? There's a non-zero probability that you've actually never been told what that condition is. Lipschitz, right? Do you remember maybe in 237 you were taught that a differential equation of a form like this, where F is Lipschitz, has a solutions exist and are unique. Okay, even if you don't know that, I just told you. And if you don't know what Lipschitz is, continuously differentiable implies locally Lipschitz, and that's all you need. Okay, so our x's are smooth, infinitely differentiable. So certainly that satisfies the conditions for existence and uniqueness of solutions of that ordinary differential equation. Okay, so I will summarize that conversation, which you may or may not have understood any part of. I don't really know what you did in 237. I will summarize that as follows. Since X is of class C infinity, it is locally Lipschitz. If you don't know what that means, it's fine. Okay, and the standard existence and uniqueness theorem, I think Mansouri covers this in 430, right? Gives. Okay, so I'm not just going to be vague here and say that it gives existence and uniqueness, because you have to be careful about that. What it does is it gives you, first of all, existence on short time intervals. Okay, so it gives the following thing. Okay, so for every t naught in the interval I, okay, so I, remember, is my interval on which my integral curve is defined. Okay, so I choose a time along the integral curve. That's going to be my initial time. It could be 0, but it doesn't have to be. Okay, so for every t naught in I, there is some positive number epsilon such that an integral curve. Oh, so I should also say, I'm sorry. Okay. And every sorry about this. And also for every x naught in M. Okay, so I have an initial time and an initial state. Okay, all right, so there's an epsilon positive such that there is an integral curve gamma, and gamma might only be defined on some small interval. And so the epsilon is giving us the size of that interval. So T naught minus epsilon to, let's say, T naught plus epsilon. Okay, so there exists an integral curve gamma for x satisfying gamma of T naught equals x naught. Okay, that's what the standard existence theory gives us for solutions of that ordinary differential equation, and therefore for existence of integral curves. Okay, so that's the existence part of it. What about uniqueness? Okay, so moreover, okay, so around every T naught I can, and with every initial condition X naught, I can find some integral curve. So let's suppose that I have two integral curves that pass through X naught at time T naught. Okay, if gamma from I into M and let's say gamma tilde from I tilde into M are integral curves for x with gamma of T naught equals gamma tilde of T naught equals x naught. Okay, so they satisfy the same initial condition at time T naught. Okay, then it must be the case that gamma and gamma tilde agree. Okay, and the best you can say, because they're defined on different intervals, you can say that they're defined on the intersection of those intervals I and I tilde. Okay, so there are integral curves for x satisfying that, and oh, so sorry. So then. Okay, gamma restricted to the intersection of the two intervals is equal to gamma tilde restricted to the intersection of these intervals. Okay. Okay, so that's existence and uniqueness. All right. Okay, so now what you can do is you can kind of argue like this. Okay, so let me not draw the manifolds and just sort of draw my curves. Okay, so what I know is that I have at a time T naught, I have gamma of T naught equals x naught. Okay, and I know that there's some little fragment of an integral curve from T naught minus epsilon to T naught plus epsilon. Okay, that I can define that goes through that point. All right. Now, I can maybe make it larger. And I know that if I make it larger, that extension to the larger curve will be unique. Okay. So sorry, I want to put that in that place. And so you can make this curve longer. Okay. All right, and at some point, there may come a time where it is no longer possible to define the integral curve. And what happens is that the integral curve might blow up to infinity. Okay, and again, I don't know what you do in your differential equations, but maybe you remember having seen an example of a differential equation whose solution blows up in finite time. Okay, so you can, very simple, it's not pathological in any way. Just take the differential equation, scalar differential equation, x dot equals x squared. Okay, you can solve that by separating x and t and integrating directly. And what you will see when you solve that differential equation is that if you solve that differential equation with, say, x of t naught equals x naught, okay, that there will be some time, possibly in the forward time, possibly from the past, where that solution of the differential equation blows up to infinity. Okay, so you can always extend these integral curves, but you may not be able to extend them to the entire real line. Is the point? Okay, and so okay, so it may. Let me just say it may not be possible to extend the integral curve gamma for x satisfying gamma of t naught equals x naught to be defined for all t in R. Okay, and again, this a simple example of that. If you haven't seen this example, I can work it out. Okay, so just that scalar differential equation will have that feature. Okay, but nonetheless, there will be some largest interval, and that interval generally will depend on t naught and x naught. Okay, and well, for vector fields like we're talking about here, you can always assume that t naught is equal to 0, but we don't need to bookkeep that right now. Okay, but there will be some interval around t naught. Okay, which is the largest one. Okay, so we're going to denote the largest interval containing t naught on which the integral curve for x satisfying the integral curve gamma for x satisfying gamma of t naught equals x naught. Okay, all right. So I have a t naught and an x naught, and I have a local integral curve defined for small times near t naught, and I'm going to extend that. Okay, and the largest interval on which that integral curve can be extended, I'm going to call I x of t naught x naught. Okay. All right. And then we're going to denote dx, okay, to be the set of all t's and x's in R cross M such that, okay, x right, so x is yes, okay, let me say it the right way. So it's such that t is in I of 0x. Okay. Yes. Okay. Good. Right. So what does this mean? So I'm going to take all times and all x's. Okay. So that if I start my integral curve, and so this is I sub x. okay? If I start my integral curve at x at time 0, I know this is what I'm defining, that I can extend that integral curve up until time t. And so the way to think about this is, given an x, okay, find the integral curve so that gamma of 0 is equal to x, okay, and then ask, is t in this largest interval for which the integral curve satisfying gamma of 0 equals x can be defined, okay? All right, so that's what that is. Okay, and then we can define what's called the flow of x, okay? And this is going to be a mapping, which I'll call phi sub x from dx into m, okay? And what this is going to be by, okay, the following equation, d by dt of phi of x of t and x is equal to x at, so I'll write this down, then I'll explain what it means. Okay, so that's the formula that defines this mapping, capital phi sub x. Okay, so how should I think about that? Well, let's write, so to understand this, okay, let's write gamma, gamma of t to be phi x of t and x. Okay. Oh, sorry, I didn't. I need one more thing here. I apologize. I need that phi x of 0 x is equal to x. Okay. So the way to think about this, as we'll see, is this is your differential equation and this is your initial condition. All right. Okay, so to understand this, I'm just going to introduce an abbreviation. Okay, so gamma of t is going to be this. So I choose an x, okay, and I only consider this thing as a function of t, and I call that gamma of t. So what I know, then I know that gamma of 0 is equal to phi x at 0 x, which is equal to x. Okay. Right, because that's what my initial condition says. All right, so my curve gamma, in other words, this is saying that at time 0, my curve passes through x. Okay, and what else do I know? Okay, well, let's take a look at this formula. Okay, this now is just d by dt of gamma of t, but that's just gamma prime. And I know that gamma prime of t is equal to x at this stuff, but this stuff is just gamma. So in other words, gamma is an integral curve. Okay, so what I've just demonstrated is that this curve is the integral curve of x satisfying gamma of 0 equals x. Okay, and so the point is that this thing, the single symbol phi t, encodes all of the integral curves. Okay, because x here is the initial condition at time 0. Okay, and then t is where you end up at time t if you start at time 0 with initial condition x. That's all this stuff says. Okay, so phi is a single object which encodes all of the integral curves of x. Okay, so thus, oops, the flow encodes all integral curves of x. Okay. Now, so the point is, you know, when you have the notion of an integral curve, as we saw. So sorry, I'll be back. What that amounts to is a differential equation. Okay, so finding explicitly what integral curves are amounts to solving differential equations. So I don't know what your state of mind was after you finished your differential equations course, whether you felt like you could solve any differential equation anyone would give you, or if you felt like no matter what differential equation someone gave you, you couldn't solve it. I don't know where you were when you left that course, but the second state of knowledge is closer to the truth. Okay, there's very, very few differential equations that you can solve, and you learned a lot of them in 237, but the fact of the matter is there's not very many more. Okay, so despite the fact that you can't find integral curves in the sense of, you know, finding explicit formulas for those, you can still organize integral curves into a meaningful object, and that object is called the flow. Okay, so that's what the flow is. So maybe let me look at the time and then give an example. Okay, so let's take let's take m first of all, equal R2. Okay, let's take my vector field x to be, so it's going to be, let me just make sure I get the signs right. So it's going to be minus x d by, minus y d by dx plus x d by dy. Okay. All right. All right, so I'm using, of course, the standard coordinates for R2. Okay. All right, so let's try to draw this vector field first. Okay. All right, so let's sort of get an idea what's going on by looking at special cases. So let's first set x equals 0. Let's first set y equals 0. And then, you know, so that'll be along here, and plot the tangent vectors associated to x along here. Okay, and so what we see is that, so y is equal to 0, so there's no x component to the tangent vectors, and the y component scales as does x. And so the idea is that these things look kind of like this. Okay. Okay, and so the idea, you know, I won't try to draw a straight line, but the idea is they scale linearly like that. Okay, and then similarly, letting x equals 0, so I'm now on the y-axis. What I see then is that integral curves point in the negative x direction, right? Because or they point in the x direction with a sign opposite to that of y. Okay, so they look like this. And again, they grow with the magnitude of y. Okay, good. All right, and then if you want to try to, you know, fill in more detail here, you can do things like this. You can look at the diagonals. Right, and then you notice that on the diagonals, x is equal to y, or x is equal to minus y, depending on which diagonal you're on. And so the size of these components are going to be the same, and then they point in a direction like this. Okay, does that make sense? So that's what my vector field looks like. Right, and then sorry, I may as well fill out the rest of it. Right, like so. Okay, now looking at that picture, what would you say the integral curves are? Circles, right? Okay, but let's actually see that. Okay, because you know the fact of the matter is, if you tweak that vector field just a tiny little bit, right, the integral curves aren't going to be circles anymore. Okay, but here they are. But let's actually make sure that we can prove that. Okay, and at the same time, we'll kind of come to some understanding of the notation that I introduced in terms of flow. Okay, so the ODE associated with this vector field okay, so I have my coordinates x and y that I'm going to use, and you know these are coordinates that are globally defined here. So this really is defining all of the integral curves of capital X. And the differential equations are okay. So you know it's very simple. You just to get x dot, you read off the component of the d by dx coordinate vector, which is minus y. So it's x dot of t equals minus y of t. And similarly, y dot of t is x of t. Okay, so those are the differential equations. Let me maybe write those in a form, which makes you believe that you could solve it. Okay, so let me go for gold to start out with. Who knows the solution of that differential equation? Okay, it's one of the kind of standard ones. Okay, yeah. That's right. So it involves sines and coses. Exactly. Okay. Good. Let me back off from that. How did you find that solution? You know, if you actually had to find that solution, what would you do to find that solution? You could do that, but actually this is a simple linear differential equation, so we may as well try to do it systematically. Yeah. Yeah, so how do you, exactly. So how do you find the matrix exponential? So I'm going to sort of boil it down here all the way down to the very beginning. Eigenvalues and eigenvectors? Okay. All right. That's good. Okay. So the point is that x of t, y of t is equal to e to the a t. So I'm just going to do something ugly here. I'm just going to put that's a times the vector x of 0, y of 0. Okay, and then e to the at involves sines and coses. Okay, so this is a particularly annoying one because the eigenvalues are complex. So that should look familiar to us, right? That's a rotation. Okay. All right, and so indeed we see that the integral curves are, so before I do that, let me then, because I've now solved the differential equation, like so. Let me write down with the exponential given by that formula. Let me write down the flow. Okay, so phi x at t and x y. Okay, so the definition of that thing is that this is going to be, if you can solve the differential equation, right, which means finding the integral curve, which we've done in this example, this is going to be the solution at time t with initial condition at time 0 being given by x and y. Okay, and so all we need to do now is just fill that in. And so it's x cos t minus y sine t, and then x sine t plus y cos t, right? And also all I did was I took this matrix and I multiplied it by x and y, because those are the initial conditions. Okay, so that's the flow in this case. And so you can see here that the flow neatly encodes two ways of thinking about that. It encodes all of the integral curves of the vector field, or in this example, because the vector field has a nice globally defined differential equation, it encodes all of the solutions of the differential equation for all of the possible initial conditions at time 0. Okay. So the notation. Instead of phi x of t and x in the book, and most often in the way people write things, they'll write that like this. Okay, I have since decided that I prefer that notation, but this is the notation that's used in the book. Okay. Okay. All right, so there's an example. Now let me look at the example in a different way. So and so I'm just going to kind of do this very quickly to get to the main point. So same vector field. But in polar coordinates. Okay. All right, so the first thing you need to do is you need to find out what this vector field is in polar coordinates. I believe that Henry did this in the tutorial. It's a change of coordinate formula, right? To go from the vector field in Cartesian coordinates to the vector field in polar coordinates is a change of coordinate formula. Okay, so I know Henry did a bunch of change of coordinate formula examples for vector fields in the tutorial, and I thought he did this one, but I'm not sure. It doesn't matter. It's just a change of coordinates formula. So in these coordinates, x is 0 d by dr, of course, right? Because the vector field clearly has no component in the r direction. Okay, plus 1 d by d theta. Okay, so the ODE is then r dot equals the coefficient of d by dr, which is 0, and theta dot is the coefficient of d by d theta, which is 1. Okay, now I definitely do not claim that that's a difficult differential equation to solve. Okay, so r of t is r of 0 and theta of t. And you have to be careful the fact that theta is only going to be defined from minus pi to pi, and so as you go through pi, you have to take care of that. But in any case, this is theta. Sorry, t plus theta of 0. Yes.
It seems like it should be dependent on pi.
It doesn't. If you work it out, it doesn't.
But we have the component is increasing.
That's your intuition. but there's we'll come. It's not a stupid question, and I will tell you how to address that. There's something that's going on in your mind, and your mind is deceiving you. But we'll talk about that later on when we revisit this Cartesian coordinate polar coordinate example in a different context. Okay, so it's a good question, but just I promise you 100% this is the right answer. Okay. I understand what you're saying. You expect the theta component to scale somehow, right? Yeah, but it doesn't. Okay. All right. And so the point is, the reason that I wanted to do this is that this ODE is not linear. Okay, so the original ODE in Cartesian coordinates was a linear differential equation. And here, by a change of coordinates, I've converted it into a differential equation, which is not linear. And so this shows you that linear differential equations are extremely special, not just because they're linear, but because their linearity actually depends on the coordinates that you choose. If you change coordinates, you can take a linear differential equation and turn it into a nonlinear differential equation. Okay, that's it for today.